Okay, so I'm happy to welcome all of you to our next edition in the webinar series on precision physics and fundamental symmetries. My name is Klaus Plaum from the Max Planck Institute for Nuclear Physics in Heidelberg, and it's my great pleasure to introduce our today's speaker, Professor Michael Block from the Gesellschaft für Schwerionenforschung in Darmstadt and the Johannes Gutenberg University in Mainz, Germany. Michael is a world-leading expert in the field of precision physics experiments in nuclear physics using atomic physics techniques, specifically penning trap mass spectrometry and high-resolution laser spectroscopy, which is also the topic of his today's presentation. Michael received his PhD at the University of Mainz in the group of Professor Günter Werth on precision laser spectroscopy. After several postdoctoral research positions, he became a permanent staff scientist at the GSI Darmstadt and later full professor at the University of Mainz in the nuclear chemistry division. He is, among others, the spokesperson of the ship trap facility, but also heavily involved in the future GSI facility called FAIR, the Facility for Antiproton and Ion Research. To the audience, as usual, in case you have questions, please type them into the chat room or the question and answer box. We will address them at the end of the talk. Michael, we are looking forward to your presentation on mass measurements and laser spectroscopy of the heaviest nuclides. The floor.
Yeah, Klaus, thank you very much for the kind introduction, and thanks to you, Stefan and Christian, for the organization of the seminar series and for the invitation. It's my great pleasure to introduce you today into the subject of my research. And I would like to start, first of all, with a short sort of acknowledgement session, where I would like to appreciate all the contributions from the different members of my groups, which are at the GSI and at the Helmholtz Institute. Of course, the various collaborations, which include ship trap and our laser experiments, Radris, the gas jet, and the recently established Fermium collaborations. You see a number of the logos from the involved institutes that are sort of spread all over the world with a little bit of a stronger participation from German groups. I have also shown here a few pictures of a couple of the people involved, but since these pictures are never up to date, this is just to give you a little bit of a flavor that this is of course an activity that includes a number of people, including PhD students, postdocs, and so on. Okay, so with this said, I would like to come to the menu of today's seminar. Since this is a very broad audience, I would really like to start with an introduction into the main research topics in super heavy element research, starting with the actual point, what are super heavy elements to begin with? I mean, how do they distinguish themselves from other nuclei? Then I want to briefly address the production of these nuclei in nuclear reactions in the so-called fusion evaporation approach. Then I will briefly go through the results we have obtained in the mass measurement program, and then discuss the atomic and nuclear property measurements by laser spectroscopy, and then come to my summary. Okay, let's go to the introduction. What is really the part that distinguishes super heavy elements, and where are they located in the chart of nuclei? Well, what you can see here is the nuclear chart, which is shown here, the number of protons to the top, the number of neutrons to the right, and we know approximately 3,000, maybe 3,300 meanwhile nuclides that have been observed in one way or the other in the laboratory, and there's about 250 roughly of them which are stable, meaning their half-life is so long that we can find them still in nature, for example. The so-called super heavy elements that I will abbreviate from time to time as SHE, or super heavy nuclei that you will realize is SHN, are the ones that are located at this sort of northeast part of the nuclear chart, really at the upper limit of existence. So why is a super heavy nucleus special? Well, if you think about the basic description that you probably learn in a lecture of nuclear physics, which comprises the liquid drop model, you will learn that there is somehow a potential. And here on the left-hand side, you see the potentials with the blue line giving you the value from the liquid drop model, and then this black line with these green shaded areas giving you the same, including shell effects. Now, if you take the blue line here at around element 106, seaborgium, you will realize that this potential well gets so shallow that in principle this nucleus would no longer be bound against a spontaneous fission. I mean, the main issue that you have to compete with is the more protons you add to a nucleus by making these very heavy elements, the stronger the Coulomb repulsion is going to get. And eventually, even as you know, already uranium with 92 protons only shows this spontaneous fission. So around 106, the liquid drop model would tell you there's the end of the story, no more nuclei can exist. But as you can see here, due to the green shaded area, even in the region of elements up to maybe 114 and more, as you will see, there is a bound potential well, which is seen here, for example, this minimum. And this is really due to quantum mechanical nuclear shell effects. So as a rule of thumb, you can say we call those nuclei super heavy nuclei that are just existing because of this nuclear shell effects and would be unbound in a simple liquid drop picture. And depending on the parameterization, this transition is maybe around 106, maybe a little less, little more, but rule of thumb around 106. You will see later on that in the chemistry community, sort of the borderline is a little bit shifted to the transition from actinides to transactinides, which is then 104, as I will show you in a moment. Now, if you go to the earliest predictions that we had, they came up with nuclear models in the late 1960s. So you see here, these are some of the very first works. I think one of the first one that was published was this work by Sobichevsky and co-workers in 1966. And at that time, the nuclear models predicted that there are really long-lived nuclei and very long lifetimes should be found in the region with 114 protons and 184 neutrons. In this little cartoon from a nuclear chart, you have to keep in mind at the time of the prediction, all these nuclei have not yet been observed, of course. There was a prediction that here some of these dark shaded squares would actually comprise nuclei that are very heavy, but would have a very, very long half-life. And that is around that time when this famous expression of the island of stability was formed. But in this particular figure that I show you from the work of Sven Gösta Nielsen and the group in Lund, you can see that this region is very localized because these light green squares that you can see are nuclei that would already have a significant spontaneous fission. So, of course, you have always competing decay modes, which is either the fission where two nuclei break up into fragments, or you have, for example, alpha decay or eventually beta decay. Okay, so that was sort of the start in the 60s. And I mean, then people had some other predictions. Here you see, for example, predictions by Fieset and Nix, or here by Rantrup and co-workers, where again in the region around 184 neutrons. So this is the neutron number, and this is the logarithm of the half-life. You see, this would be the age of the Earth. You see a couple of long-lived isotopes of curium and other long-lived actinides. And you see the prediction at the beginning of the 1970s was still there are maybe very long-lived nuclei that could have a lifetime of more than the age of the Earth. And that actually triggered the search for super heavy elements in nature, some of which are still going on today. However, all of them have not led to a positive result that was unambiguous. And in particular, colleagues with accelerator mass spectrometry have investigated a large range in mass, and for the, let's say, on the level of sensitivity that they have, which is very high, they have at the moment ruled out the existence of such nuclei in a reasonable mass range. Now, in a more graphical representation, then the nuclear chart was depicted like this. This is by Flerov and Ilionov. And you see here the known nuclei would be here in the lower part, and you would have some peaks for doubly magic nuclei like calcium, tin, or lead. Then you would have a first gap where you would have the region of the actinides. And back then, of course, the island of stability of super heavy elements was far away from the known territory of nuclei. Now, of course, as of today, as many of you probably know, we have synthesized up to 118 elements. The heaviest element is 118 named organezon, and the other ones 117 tennessine, 116 livermorium, 115 moscovium, 114 flerovium, 113 nihonium, 112 copernicium, and so on and so forth. All of them have been synthesized in tremendous effort. Some of them took really several months of beam time for 1, 2, or 3 atoms. And so now we have, of course, seen that many of these nuclei indeed exist. So all these yellow, green, and some of these reddish squares are really nuclides that we have obtained. The blue color that you see in the background is the increase in binding energy due to nuclear shell effects. And you can see the darkest blue area would be the region near 184 neutrons. And this is yet again the region where in the past people have predicted the island of stability to exist. So we have been approaching it, but we are still a couple of neutrons shy from the actual number of 184. Now, is there really an experimental indication or evidence that something like an island of stability really exists? Well, in fact, let me first briefly introduce some of the key people before I come to that point. So here on the left side, you see from the discovery team, Sigurd Hoffmann and Gottfried Münzenberg, who have been involved in the element discoveries at GSI. In this ceremony, they have a meeting with the mayor of the city of Darmstadt, because Element Darmstadtium, of course, brought this city to the chart of nuclei and the periodic table forever. You see Kosuke Morita from RIKEN, the leader of the discovery team of element 113 here, shortly after his third atom was announced. And here you see a couple of the discoverers in the conference last week here, Yuri Oganesian, the person who gave the name to element 118. This is our Japanese colleague who was part of the discovery team here for element 113, and again Gottfried Münzenberg. And here you see Peter Armbruster, the person who has really established the Superheavy element program at the GSI in the beginning of the construction of the facility. Okay, now let me come back to the question about approaching the island of stability. So here you see the shortest lived and most neutron deficient copernicium isotope that we know today. That was actually the one that was discovered when the element was discovered, was first observed. And this half-life is a little shorter than a millisecond. And here we are having 165 neutrons. The most neutron-rich copernicium isotope that we know today has 173 neutrons, and you see already here the half-life goes up to about 28 seconds, which is a factor of 40,000 more in half-life with only 8 additional neutrons. Now, of course, the question remains, what are we going to see if we add another couple? In this case, it would be about 11 neutrons that we need to add to reach number 184. So there might still be a significant increase in half-life. Whether this is long enough that you would find a super heavy element in nature, I will show this in a moment, has shown to be unlikely. Now here is a nuclear model calculation of the spontaneous fission half-life. I mean, many of the models come to similar conclusions, so I just picked this one as an illustrative example. This is work by Andrzej Baran and collaborators, and this was published in a special issue on super heavy elements that was published in 2015 in Nuclear Physics A. And again, the thing that you observe is here, the dark red region is the highest spontaneous fission lifetimes. And this is really, once again, the region around 184 neutrons. But of course, spontaneous fission is then not the only relevant decay mode. You have then to, of course, also add alpha decay and other decay channels. And if you then combine it, for example, also with the alpha decay, that would then be the dominant maybe decay channel besides beta decay and electron capture, you find around 184, there's a small region where you have really extended lifetimes. But if you do the math, you're talking rather something about maybe 100 days that would be still there, not maybe billions of years as it was predicted at the end of the 1960s. So I would say one can say there is indeed a significant increase in half-life in the region of super heavy elements. And the further we approach neutron number 184, the longer the half-lives are going to be. But we do not expect at the moment that we will see long half-lives close to the long-lived actinides that we can still produce in macroscopic quantities. So the main idea about the island of stability is enhanced stability against spontaneous fission, but still moderately long-lived or short-lived radionuclides that would disintegrate. Okay, so that's the story about island of stability and super heavy elements. Now, general story about limits of stability. As I will talk about mass measurements, of course, one of the things you can derive from a mass measurement are proton and neutron separation energies. And here you have in green the nuclear chart of the known cases that we have observed in the laboratory. And here the red lines give you somehow the boundaries. In this case, it's a nuclear model based on energy density functional, and this is taken from a work published by Jochen Erler back in 2012. But the interesting fact is, if you now look in the area of super heavy elements, you will find something quite neat, because in the element Ionization, we at the moment know just one isotope, which is very neutron deficient here on that side, and according to theory, we would have about 100 isotopes of Ionization that should be in principle existent, but have not yet been, of course, produced and will not be produced in the near future because of the lack of suitable beam target contributions. But at least from a theory perspective, there's a wide range in the chart of nuclei of investigation to be made, and discoveries are, of course, there for the taking. Now, as I said many times, the big story for the stabilization are shell effects, nuclear shell effects. Now I have a comparison here where you see different nuclear models describing shell effects in light nuclei. So these are tin nuclei. So you have here on the left side a maximum, which would be the tin 100, which is known to be a doubly magic nucleus. And here on the right side, you would have a tin 132 as another doubly magic nucleus. Without going into any details of the models I've shown here, you see in all the models you get a very distinct feature that they are, so to say, what has been called a magic number. So for a very specific proton-neutron configuration, you get this enhancement in binding energy where this shell closure is going to happen. And if you look in the same way in the region of the heaviest nuclei, you see that this looks qualitatively different. Instead of having really a distinct magic number, we have in more or less all models rather extended areas where the shell effects show an impact. And this is also reflected in the half-lives that I showed you a moment ago. So one of the things we want to study with mass measurements, and of course also with nuclear spectroscopy, is really how much do these shell effects extend in proton number for a given neutron number or vice versa. And here you see another representation, again, very different models. And you see here, this is single particle energies. Here it's a little bit more simplified. So maybe let's look on the right-hand side for the moment. The main point is there you see certain gaps. So here you have single particle energy. And whenever there is a big gap, this is usually the case of a shell closure, as we call it. And here you see on the left-hand side, the spin-orbit coupling is stronger. And here on the right-hand side, you see the spin-orbit coupling is weaker. And you see that the strength of the spin-orbit coupling is one of the factors, for example, that determines whether such a gap emerges and where this gap in neutron or proton number actually shows up. So this is somehow the physics we are dealing with here. Now let me go to the more atomic and chemical properties. So I'm choosing the representation of the well-known periodic table. And as many of you probably remember, last year we were celebrating the International Year of the Periodic Table as announced by the United Nations, and they created this logo that you see here on the right-hand side. And again, here you see now the representation where you have the super heavy elements here highlighted in this red bar. And this would be in the chemical perspective, the trans-actinides. You see the actinide series down here. And then after the actinide series, the trans-actinides. So from the chemical perspective, we start calling element Rutherfordium up to element Ionization super heavy elements in this terminology. Now, what is the story about atomic physics and chemistry in super heavy elements? Well, it is about, for example, relativistic effects. Here you see an example for uranium in a calculation by Jean-Paul Duclos, where you see, for example, that orbitals like s orbitals or p orbitals, they really show a contraction in the relativistic case, whereas, for example, d and f orbitals are usually expanding. This is also shown here in the calculation of a wave function here in the blue line. This is for gold, and in the red line, this is for röntgenium. So these are elements in the same group. And you can see that here the ground state, this is a 7s configuration. You see that the maximum here in this curve is somewhat shifted compared to the case of gold. So yet again, you see this contraction due to relativity. Another interesting example is shown here. This is a calculation by Paul Jerabek that was published in Physical Reviews a couple of years ago, which compares noble gases. This would be organeson, which potentially is a noble gas. We don't know that yet. And then you have radon and xenon. And then you see, for example, that what we usually call a fine structure splitting is not a perturbative small part anymore, but the splitting here in the 7p in organeson is around 10 electron volt, which is quite a strong case. Another important remark, of course, if some of you are dealing with quantum electrodynamics in systems where usually Z alpha is small compared to 1, this is of course not the case for elements with a Z number on the order of 100. So at this point also quantum electrodynamics effect start playing a role. And this of course we can all study by atomic physics technique, as I will come back. So some of the key questions that we try to address are still today valid. And this is first and foremost, where is the end of the periodic table or the nuclear chart, if you wish, in atomic number and mass? So what is really the heaviest element that can exist, which is basically governed by the heaviest nucleus that will not undergo fission in a very short time? What are the properties and boundaries of this predicted island of stability? And for example, what will be the longest half-life that we will observe? Related to astrophysical scenarios and nuclear synthesis, of course, there is an ongoing question, somehow not fully settled. Could these super heavy elements be produced, for example, in an R process and survive maybe somewhere in the universe, if not here on Earth? And for the chemistry and atomic physics part, how do relativistic effects change or affect the architecture of the periodic table? Okay, now in order to make a study and a precision measurement, first we have to produce the element of interest. I will be relatively brief here, but keep in mind it is a challenging part, because what you can do and what you do in most of the cases so far is you do what we call a nuclear fusion evaporation reaction. So I have depicted here the cartoon-like example for the discovery of element 112, where you would take a zinc nucleus, zinc 70, and try to shoot it on a lead-208 target. And if you do it with the right velocity, which is about 10–15% of the speed of light, you might be able to form a compound nucleus that will then form a de-excite and then form an evaporation residue. In this case, that would be a copernicium that evaporates one neutron to reduce its excitation energy. From our precision point perspective, the key part is this is a nuclear reaction which takes place at high energy. So we are talking about few hundred MeV, let's say 200 MeV or something like this beam energy. And we want to get the ions and particles later on to low velocity or even at rest. The other important part is we have only a certain combination of beams and targets that we can make use of. So we cannot produce arbitrary elements of interest, but only a certain selection. And we have to have high intensity beams where beam intensities are on the order of close to 10 to 13 particles per second. Yet the yield that we get is tiny, meaning high rate experiments are usually in the region around element 102, where we can produce a few particles per second. It goes down to a few particles per day. And in the most extreme case, we are dealing with 1 particle per week in a 24/7 irradiation of a corresponding target. So the challenge number 1 is to deal with very low rates and with a very low total number of particles. So in all cases, we need to be efficient and sensitive. Now, where do we do our experiments? We do them at the GSI accelerator facility in Darmstadt, Germany. Here you see on the left-hand side a person inside part of the UNILAG linear accelerator. So we have a linear accelerator here, which accelerates everything from protons up to uranium to energies on the order of, say, 10 MeV per nucleon. The parts with the synchrotron and storage ring are not relevant for my talk, so I will not talk about that. But of course, I want to mention that at Darmstadt, we are building the FAIR facility, which is an international facility. And here you see, for example, the construction site for the new synchrotron accelerator. Here you see the construction site looking at the present GSI facility, which you can see here in the back. And so in the future, FAIR will be a leading international facility for nuclear physics and of course some other physics topics. It's a large international collaboration and a lot of money is involved. There are 4 science pillars, which include atomic physics, biophysics, plasma physics, material research, nuclear and quark matter, nuclear structure and astrophysics, and of course hadron structure and dynamics. But I will not go into more details. I just wanted to make sure that you are aware of this development. I will show you the part of the facility that deals with the super heavy elements. And this is mainly using the UNILAC here, starting most of the time from the ECR source on that side or from the penning source down here. And the beam then goes straight to where this is shipped, which is a separator that we use before our experiments. Now let me start talking about the mass measurements. So let me briefly go back to the story of the shell effects and the decays. So again, you see this part of the nuclear chart that you have seen before. So in this case, the colored nuclei that I have added here in red are the ones that we have measured or whose mass we have measured with ShipTrap a few years ago. And in this yellow and greenish color, you see other nuclei that are connected to the ones we have measured directly, for example, as depicted here on the right side, by alpha decays. That means, for example, Darmstadtium 270, element 110, after 1, 2, 3, 4 alpha decays, ends up in Nobelium 254, where we have measured the mass directly. That means, of course, you can use the precise direct measurement, combine it with the alpha energy measurement that you have, and then you can even fix the mass up to Darmstadtium 270. In addition, as I talked about before, we can use the masses to derive binding energies and then study the nuclear structure evolution and, of course, benchmark and potentially improve nuclear models. Here you see as an example of derived properties indicative of shell closures, again, this property which is called the 2-neutron separation energy. It's basically a mass difference of a nucleus and a neighboring nucleus with a difference of 2 neutrons. And this is shown as a function of neutron number. And you see this is relatively smooth functions, but you can see, and that's even more pronounced at certain regions, at certain neutron numbers, you see this sort of a kink in the plot. And this is usually indicative of a shell effect or a potential shell closure. A weaker one you can see here around 152 neutrons. So these are structural effects that you can make or visualize from mass measurements. Here you see it a little bit more pronounced. This is basically the derivative of the previous curve, and then this is shown over a wider range. So here you see this peak here that is reflecting the well-known shell closure in the doubly magic lead 208. This is again our 152 region, and this is the 162 region. I mean, for 184, of course, we do not have any data yet. We would expect a peak which is a bit lower than the lead one, but a bit higher than the 162 one to show up here on that picture. So these are the kind of informations we can get from a mass measurement. Mass measurements today in a so-called direct technique are usually done in a penning trap, which is familiar to many people in the audience, I assume, or alternatively, so this is a penning trap here where a single particle is combined in a magnetic field and an electric field, leading to a trajectory which is depicted here on the right-hand side. And the main information here that we need to know for a mass measurement is that the cyclotron frequency, so this angular frequency, this radial frequency that is depicted here in this black trajectory, this depends on the charge, the magnetic field, and the mass. So this gives us a handle on mass measurements, and what has come in lately is a variant of the so-called time of flight approach, where you have so-called multi-reflection time of flight spectrometers, where the ion bunches are oscillating between electrostatic mirrors, and then after a certain time of flight are hitting a detector at different times, and the time difference is indicative of the mass to charge ratios. These are the two techniques that are also applied in the heaviest elements. Of course, the penning trap is usually superior in resolution, as I will show you, and therefore can be used also to study excited nuclear states, so-called isomers. Well, ShipTrap was the first installation where measurements in a region above atomic number 100 were made, starting at element 102. Key point is in the beginning, you have to slow down your reaction products from the nuclear reaction to small and low energies, and this we are doing in a buffer gas filled cell, which is operated at a temperature of 40 Kelvin. And here you see sort of a little cartoon, how the particles sort of expand when they are stopped. You can use electric fields inside the system to get the particles out in about 10 to 100 milliseconds. And then you have a couple of transport units, which are radio frequency quadrupole structures, which can be operated as ion guides, or you can cool and accumulate particles here in a so-called cooler buncher. And then you inject into the panning trap, which is inside the superconducting solenoid. And here you see this solenoid in the actual photograph. Here you see the cryogenic gas stopping cell, just to give you an indication of this setup. Now, with this setup, we have since a few years started to use a phase imaging method that we have actually developed in ShipTrap a few years ago, proposed by Sergei Eliseev now in Heidelberg. And so what you do is you take an image of the ion motion. If you excite the ion to a certain radius, you will get a point on your position sensitive detector, which is depicted here. And then if you repeat the same thing after a couple of rotations inside the trap with a little longer storage time, then you will be able to observe a third point. And having the center point and the position or the phases of the two excited ions will allow you to determine this phase angle. And of course, if you know the time difference after a certain time in the trap, you can calculate the frequency based on the simple relation between the phase phi and the frequency here as you know it. The important part is that the uncertainty of the frequency actually scales with delta R, which is the radial spread, sort of the size of the blob on your detector, and is inversely proportional to the radius. So in principle, if you go to a large radius and to a small radial spread, which you can achieve, for example, by cooling, you can increase the resolution. And of course, you can somehow beat the Fourier limit. That was really the limit in the conventional techniques that have been used for many years in the past. I will show you some examples of the performance of this method shortly. Here you see an image of the detector, and here you see an image actually of the ion motion. This is, in this case, the magnetron motion for different phases. So this would be the center spot, and these are the different phases. I mean, the 8 millimeters that you see here are 8 millimeters on the detector, and the magnification is about a factor of 20, as it is written here. So a 20th of that is the actual radius inside the panning trap prior to ejection. Now, as I said before, this method was pioneered at ShipTrap and has meanwhile become the standard approach in radioactive beam facilities all over the world. In 2018, we have used this method under online conditions in a very successful campaign. What I have plotted here is the nuclei that we have measured. So in this vertical axis, you see the production cross-section. So this is somehow the rate that you get. So the lower this gets, the lower the rate is. The length of this area that I have shaded here is the time we had to spend to perform the corresponding measurement. And then you see here this dashed red line. This was the limit that we had achieved with ShipTrap back in 2010. We have used two different primer beams. That is just a detail for the experts, calcium-48 in the beginning and titanium-50 at the end, under not ideal conditions as it sometimes happens in an accelerator. And as you can see already visually here, this is, for example, Rutherfordium-257, that is C number 104. That was the most challenging measurement, where we had in the end only 5 ions in total detected, and the rate was about 1 count per day. Nonetheless, we can determine here a mass value, but we have, as you see, also measured a couple of other cases, and we have really pushed our previous limit significantly down. One of the cases I would like to highlight concerns 255 Lawrencium, and you see this has a ground state which is a lifetime of 30 seconds, and there is an excited isomeric state which has an energy of only about 37 keV, and the half-life is 2.5 seconds. And so this is a very low mass difference at mass number 255. Nonetheless, with this phase method, we can actually resolve it. So what you see here is the center position, and then here you see 2 blobs. This entire picture corresponds to a 10-hour measurement, And you see here on the left-hand side, this is the blob that corresponds to the ground state, and this is the one that corresponds to the isomeric state. And if you compute the mass resolving power, you end up at a number of 10 to the 7 in the accumulation time of about 1 second as the ion spent in the trap per cycle. In a direct comparison to the previous campaign where we had a different technique, so we get a different signature. Here, this minimum is where the cyclotron frequency is reached. You see then we had only 2 ions per hour in the detector. Meanwhile, we have been able to improve the efficiency to detect in the same time 14. The mass resolving power, I have said, was increased in this case by a factor of 10. And the statistical uncertainty is now only a few times 10 to minus 9 compared to about 10 to minus 7. And this is even done in only 10 hours compared to 30 hours of measurement time. So this is quite an improvement. And this is just an overall sort of summary of the results of the various nuclei. And this is a relative precision, as I said, statistical precisions of a few times 10 to minus 9 in the best case, sometimes a little less due to statistics. If you now look into the chart of nuclei, you can see here somehow all the mass measurements that have been published. So these are the ship trap data here shown in red, some additional data from RECON. Of course, our colleagues at RECON have meanwhile done additional measurements in the dubnium area, which as far as I know are only found on the archive. So I have not included them here, but they have been of course performed. And on the long-lived actinides, we have the trigger trap in Mainz, where we of course also contribute some measurements. Okay, so that was for the moment the part about the mass measurements. So let me now come to the laser spectroscopy. In laser spectroscopy, you see the nuclear chart is a little busier. So this is the nuclear chart where the red shaded areas indicate regions in which laser spectroscopy has been performed. Of course, this is largely governed by the production scheme. So a lot of the red areas are nuclei that are available at so-called isol facilities as low energy beam of good beam quality. That also means that, of course, the area up here is pretty much empty. If you look more closely, the area up here, so this is all the nuclei that we know here. All the nuclides are shown as a square here, and the colored squares are the one where laser spectroscopy has been performed. The work we have performed in Nobelium that I will discuss in a moment is up here. The offline measurement of 255 fermium that was performed in the bucket group several years ago in Mainz is shown here. And as you will see later in my talk, we have been able to add a few more dots here in this area. I mean, bottom line is in the actinides, not so much is done. Most of what is done in these nuclides are cases where you have long-lived actinide isotopes in picogram to milligram quantities that allow offline measurements. Here you see the known and published atomic levels that are known in the actinides, starting from actinium, where not so much is known, but of course things like thorium, which are nowadays very popular, of course uranium. There is quite a lot of data, but you see as soon as you reach Einsteinium and fermium, everything becomes very limited. And here at the end, in Lawrencium, we of course have only theoretical predictions. So you see there is a lot of work to be done to find some of these levels and measure some of the properties. So this is the situation as we have it today. One of the properties that is of course of interest is the so-called first ionization potential. Here you see the first ionization potential for all elements up to fermium, where it was measured. And of course you see that the noble gases are giving you here these peaks. Of course you see that there are also that sort of
Michael, I can't hear you any longer. Stefan, can you hear him?
Same for me.
What about the others?
But the seminar is still live, so.
No audio, Zilla, thanks. Michael, can you hear us? Oh, he's frozen.
Hear me again?
Yeah, okay. Yes, you're back.
Okay, I don't know what happened. Yeah. So do you see the slides again?
No.
Not yet.
Okay, let me go. One moment.
Okay.
Yeah.
We can see your slides,
Yeah.
but not in full screen mode, Michael.
It's not full screen?
No, same problem which we had when we were doing our test session.
Okay, I think now you should have it in full screen.
No.
No?
No.
How about now?
No change.
Okay, let me try to check again. So, do you see it?
Yes.
Yes.
Okay, wonderful. Yeah, sorry for this. I don't know what had happened. Okay, so now, I don't know, did you see, I think that is the slide when I was kicked out, right?
Yes, Michel.
Okay, so I was just discussing the accuracy in the measurement of the actinides. And yeah, so, okay, now generally what is the properties from the nuclear side that we can see from laser spectroscopy? This is indicated here. So if we have an atomic transition, then we can see, for example, a shift of this transition in different isotopes. And from this isotope, we can learn something about the mean square charge radius. If there is a nuclear spin that is non-zero, then of course we can obtain a hyperfine splitting. And then from the splitting pattern, we can learn something about the nuclear spin. We can learn something about the magnetic moment and about the quadrupole moment in case there is one that is not zero. In the rare elements or rare isotopes and in the super heavy elements in particular, as I said before, we have to deal with very low production rates, a low amount of number of total atoms detected, and as I said, also high energy production. And another inconvenience, we do not have stable or long-lived isotopes usually to test our method in advance, so we have to work with the chemical homologues. As I said also a few times during my talk, we always need sensitive and efficient methods. And if we have no experimental evidence, we need atomic theory to give us a guidance where to look for atomic transitions. And for some nuclear properties, we will find out later that a high spectral resolution will become important. So there is one method that is quite established. This is the so-called resonance laser ionization. And this comes in different varieties. I have shown a few representative examples in this cartoon on the left. So here, this is a two-step excitation scheme starting from the atomic ground state. You take a strong, loud laser transition into a first excited state. And then you take various ways of getting the excited atom ionized. The idea is that you want to create an ion because in many cases the detection of an ion will be more efficient than the direct detection of the fluorescence that is of course emitted here in the de-excitation process. And so you can either do this in a non-resonant case with a very high power laser. You can of course try to find an auto-ionizing state if you have one, or you might go to high-lying Rydberg states from which you can have, for example, ionization by field effect or collisions or something else. And so these are the typical ways that this method is applied. And this is also used, for example, in ultra-trace analysis. For searching levels in unknown elements that I will discuss, we will mainly use the conditions that are shown here on the left side, where really only two steps are given. So the method that I'm going to explain you in a moment is the so-called radiation detected resonance ionization, where we produce atoms. This entire environment that you see is in an argon gas at 100 millibar. And then the ions are entering the setup, and afterwards they are accumulated on a filament, which is a thin wire, by the help of electric fields. Of course, when they hit the filament, they will neutralize, which is what we want, because we want to ionize the atoms. Then we heat the atoms and fire, in this case, 2 laser pulses. If the laser frequency matches the atomic transition, then we will have an ionization process. We can then transport the ion to a detector. And once we are at the detector, we wait for the radioactive decay to occur, and we get a signal. The radioactive decay has the benefit that we get a better discrimination of background events. So in case of the element nobelium, we have an excitation scheme that you see here. On the left-hand side, you see these rectangular areas, and in these rectangular areas, these are theoretical predictions from various methods. I mean, I don't want to go into the detail of this method. I just want to mention that what you see here, let me rephrase, so the size of the rectangle represents the uncertainty of the corresponding method. And if you compare this to the bandwidth of your laser and the step size in your scan, then you will find that you need about already something like maybe 5,000 steps to cover the uncertainty of the theoretical prediction. Oh, now everything's accelerating a little bit. Sorry for that. Yeah, so that means you scan, and maybe one step can take up to 5 minutes. Yeah? So that is a very lengthy procedure, and these are really relatively reliable and accurate calculations. Good. Now let me continue and show you the results. So in about 2015, we had a first breakthrough where we found the resonance for the first time. So we found 1 atomic transition in the element nobelium, 102. And so afterwards, we were able to improve this measurement. And here on the left-hand side, you see the measurement for different isotopes of nobelium, 255, 254, 253, and 252. The lowest yield that we have dealt with was about 0.05 atoms per second in the case of 255 nobelium. So such a hyperfine spectrum takes almost half a day to acquire. At the same point in this measurement, you can already see right away that the center of gravity of these transitions that we see are shifting, and this is the isotope shift I was mentioning before. So the different number of neutrons that we have in our nucleus modifies the charge distribution, and this is then seen by the change of the electron energy level that we can measure. You also see, of course, that in the odd nuclei, where we have a nuclear spin that is non-zero, we get a hyperfine splitting. So this is 255 nobelium. Sorry, something is going on here. And 253 nobelium. And so here we have a splitting. In this case of 253, this hyperfine splitting is not fully resolved. So on the left side, you can probably see there are 2 lines overlapping. Nonetheless, you can determine the hyperfine parameters A and B that allow you to determine the magnetic moment and the quadrupole moment. Now here I have a nuclear model showing you the deformation. I would like to remind you that the nuclei we are talking about are in this wide region of prolate deformed nuclei that you see here in the middle of the screen. And so we have really a deformed nucleus. That is what we want to see also in the change of the charge radii. So here you see from the, here you see from the model calculation the beta 2 parameter, which is the deformation. And so you can see at neutron number 152, this deformation actually is maximum. And the change in deformation in the neighboring isotopes is relatively small in this particular model. What you can also see in this color plot is the charge distribution of the nobelium nucleus. And what is interesting to see is something that is called a central depression that is predicted by several different nuclear models in heavy nuclei. That means the charge distribution in the center has a little bit of a dip. Yeah? And this is something, an effect in Nobelium is on the order of 10%, and it is expected to become stronger in even heavier elements. Now, the charge radii that you can derive from the isotope shift is shown here on this plot for all the actinides, and the red data points are the ones for Nobelium. And you see the lines that are given here are theoretical calculations from nuclear models using an energy density functional approach. And it is actually nice to see that there is quite a good agreement between the experimental data and the calculated values in almost all the actinides shown here. Very recently, actually, in this year during the COVID lockdown period, GSI was one of the few, if maybe not the only, nuclear physics lab that was running even a beam time. And we were among the experiments that were able to perform experiments. And this was allowing us to perform the measurements that you see on the left-hand side. If you would have talked to me about a year ago, I would have told you the fermium isotopes 250, 249, and 248 are really inaccessible for laser spectroscopy because they cannot be produced directly with a very reasonable reaction. So this is not in reach. In fact, now we had a very good idea. We can actually produce them indirectly via the alpha decay from the Nobelium isotopes that we have measured before, as you saw in the previous figure. So this is now really a decay, so you can produce so fermium is element 100, so it's of course the alpha daughter of element 102. And so you can really produce various of these isotopes from Nobelium, yes? And so 252, 253, 254. And this allows you to actually still perform laser spectroscopy. And as you can see here, even in the 249 fermium, you can see somehow a part of the hyperfine splitting, of course, by far not resolved, as the hyperfine structure is very complicated, as I will show you in fermium isotopes in a moment. Something else that we have done from the atomic physics, in this case again in Nobelium, is a ionization potential determination based on a Rydberg series. So what you can see here is a Rydberg series. So each of these colored sort of needle-like structures is an individual Rydberg state that had been found, and there's about 35 of them identified, and that's led to a determination of the ionization potential. The result is shown here. So on the left-hand side, you see a comparison of the actinides ionization potential in red compared to the lanthanides shown in blue. So you see qualitatively they are really behaving similar, like it's expected for the homologue. And in the case of Nobelium, there are some calculations for the ionization potential by Borszewski et al. There was a relatively old extrapolation by Sugar, and there was a surface ionization method employed by Sato and collaborators, and they all come up at around 6.63. With the laser spectroscopy, of course, we can determine this with far more precision. So you see a couple of more digits. And so this was one of the atomic properties that we could determine for Nobelium. So this was all work that was done online with low rates at the GSI. But as I said before, there is of course a possibility to perform laser spectroscopy on long-lived actinides. So we started to team up with a group of Klaus Wendt, Tom Albrecht-Schönsaat from Florida State University, and Christoph Düllmann, whose group is very much expert in making radioactive samples. And so Tom Albrecht-Schmidt was able, Tom Albrecht-Schönsaat, I have to say, he got sort of married recently. He actually was able to provide us samples of Einsteinium and Fermium that have been produced in the high flux reactor in Oak Ridge, Tennessee. Well, in fact, we received a so-called Fermium sample, which contained, besides Fermium isotopes, a lot of Einsteinium. But in our case, that is a positive effect. And these measurements were performed offline at the Risiko separator of Klaus Wendt. And this is a hot cavity system, where in a hot cavity ion source, you evaporate the atom of interest, and then you use laser beams for a resonant ionization. After ionization, you can, here, so the atom beam comes out, the ions are created here in the exit region, and then you have a mass separator, after which you can detect the ions separated according to mass. And this is, of course, a well-known approach. And here you see one of the many spectra that we were able to record, in this case, Einsteinium-254. And you can see by this complicated spectrum already that the hyperfine structure is really not so easy. We were also able to measure the Einsteinium isotopes 253 and 255. Some of them were available in quantities on the order of a few picograms to nanograms, so something like 10 to 9 to 10 to 10 atoms usually. And we had also the chance to measure Fermium 257, and this is actually shown on this figure. So on the upper panel, you see the isotopes that I showed you before. So these 3 isotopes here had been measured online at the GSI. This is the data that Bakke obtained several years ago, also in Mainz on 255 Fermium. And this is the recent data that we obtained in 2019 here in Mainz. So we have now added information to a couple of new Fermium isotopes. And once again, you can see the isotopic shift here very clearly. And also here we can say for the moment, in the present status of the data analysis, there's a good agreement with spin parity assignments from literature. Some of the data which had been known are also in good agreement. Of course, many data are new. And the ones that we have new, we can at least say are in good agreement with theoretical predictions and calculations. Okay, with this, I would like to come to my summary. I hope I could show you that high precision mass measurements with panning traps are very powerful tools to investigate radioactive nuclei, and that they can meanwhile be applied to super heavy nuclei such as Rutherfordium element 104. We have a high resolution or high mass resolving power, to be more precise, that allows us to find excited nuclear states, so-called isomers, with excitation energies on the order of 35 keV. With the online laser spectroscopy, we were able to address a couple of Fermium isotopes for the first time and expand our studies in Nobelium element 102 in online experiments at the GSI in Darmstadt. And in offline measurements that we performed on long-lived actinides with picogram quantities in Mainz, we could add some data for Fermium and Einsteinium isotopes. All in all, I can say we have really nice and new opportunities to obtain properties like binding energies, informations on the shape and size of nuclei, on the electromagnetic moments, and many more ground state properties that you can derive. In addition, we always have some technical and methodological developments going on in order to extend the sensitivity further so that we can reach even more exotic and heavier elements. And with this, I would really like to thank you for your kind attention.